Good morning. We'll continue with our module number 1 today. And in this class, we'll be looking at 2 points. First is the boundary conditions. And the next is Laplace or Poisson's equations. So we'll be looking at both of them. The boundary conditions actually we could have done in the next module, but I think we will do it in electrostatic itself because it is related to electrostatics. Okay, so there's a derivation for boundary conditions, so please be careful in the lecture. Okay, so before looking into the boundary condition, let's recap some things. We had defined something called as electrostatic potential. It is defined as V is equal to minus integral E dot dl. Okay, and we told that if you have a path and there's a field crossing this path, and the path is from points A to B, if you want to find the work done in moving a charge from A to B, you consider small strips of length dl and you integrate the field E for each distance E dot dl. And if the external field is doing the work, this will be a minus quantity, and this is the potential difference VAB. And we also told that this is actually independent of the path. So if I form a closed path, means something like this, I close this path. Okay, the electric field is still there, crossing the whole thing. So if I go in the reverse direction, that is from B to A, so in this direction, if I want to do some work, then VA will be equal to E dot dl without the minus sign. Or you can say VAB is equal to minus VBA implies VAB plus VBA is equal to 0. So the potential around a closed path implies you can say the potential around a closed path is equal to 0. That is the result. Why? Because when we travel from A to B, you have one potential. And when you travel from B to A, you have a potential which is minus of that of from A to B, because the electric field doesn't change direction. So if you want to do work to move any charge from A to B, when we are moving from B to A, the work will be done by the electric field. So electric field will automatically do that work. And since both are independent of path, the potential VA will be equal to minus of VBA. So this is an important result that we have seen. So basically I can write for a closed path, E dot dl is equal to 0. This is one result. Okay. And then we'll also make use of the Gauss law, which says the net outward flux is equal to charge enclosed, for which we have derived an expression in terms of divergence del dot D is equal to rho V, which is the volume charge density. Or I can always say around the closed path D dot ds is equal to Q enclosed. Okay, this we have already derived. Okay, if you want to derive this, you can put a volume integral on both sides of this equation. and you know, okay, I'll just do it. So you have, if you put a volume integral, del dot d dv is equal to integral rho v dv. This is actually the charge enclosed. Okay, and this you can write it as using divergence theorem. This is integral d dot ds. This is q enclosed. So these are the things that we have seen in the previous classes. So we will make use of these two equations. One, the equation of the Gauss law, and the other that the vector potential or the potential electrostatic potential around a closed path is equal to 0. Okay, fine. Now let's come to the boundary conditions. Now let's define what a boundary is. Okay, so till now whatever we have seen, we have considered the medium as a single medium. We said that, okay, there is only one medium, and inside the medium, if there is charge, what are the effects of the charge? How is the electric field varying? How is the potential varying? So basically, we are considering only one single medium, which has some permittivity epsilon, which has maybe an electric field crossing E, which has some potential V, which has some charges Q1, Q2, Q3, etc. arranged. We have considered only a single medium. But practical scenario, you will not have a single medium. Instead, the medium might be combined with a different medium. For example, I have a medium here like this. Let's say this is some dielectric. Okay. And it might be interfaced with a conductor. Okay. The lower part of the medium is dielectric, upper part is conductor. A simple example is your capacitor. In your capacitor, you have a metal, or you have two layers of metal, and in between these two layers, you have some dielectric here. So this is a capacitor, just to give an example. So you see that there is a boundary between the dielectric and the conductor. So basically, this is that boundary. Okay. Similarly, you see in this case, this is that boundary. Now, because of this boundary, whatever the electric field, the potential, or the electric flux density, whatever is there in one side of the medium, it will change when you cross the medium. For example, if I say the electric field E, E1 is here, it has with permittivity epsilon 1, and it has some electric flux density D1. When you cross this medium to the conductor, it might have a different electric field E2, a different permittivity epsilon 2, and different flux than electric flux density D2. Okay, that is when you cross the, this is the, when you cross that boundary. So boundary you can say as the interface between two different mediums. It need not be a conductor and a dielectric. It can be two different dielectrics. So this can be another dielectric with a different permittivity. Or this can be free space. So all these possible combinations can occur between these two medias. So what happens to the electric field, the electric flux density, when you cross the boundary? Or how will you relate E1 and E2? How will you relate? Is there a relation? Or how will you relate D1 and D2? Is there any relation? And all these are derived using the boundary conditions. Okay. So as I said earlier, the boundary can be of any form. It can be a dielectric conductor, conductor free space, conductor, conductor, all these things are there. Okay. So first we are going to look at a dielectric boundary. Okay. So in a dielectric boundary, let's say this is the boundary. You have a dielectric here and another dielectric here. Okay. So in the first dielectric, let's say my electric field is E1, my permittivity is epsilon1, my electric flux density is B1. In my second medium, let's say my electric field is E2, my permittivity is epsilon2, and electric flux density is D2. Okay. And you know the electric field and the electric flux density is vectors. They have some directions. Okay. So the electric field direction of in the first medium might be something like this. And similarly, the electric field direction in the second medium will be something like this. We don't know, some direction. But whatever be the direction, if any vector quantity electric field is a vector quantity. So any vector quantity can be decomposed as sum of two perpendicular components. That is the general rule. So what we are going to do is, you have an electric field like this in any of the medium. You can decompose into two different components along vertical and horizontal directions. So let's say this is E1. So I say I can decompose into two components. One is horizontal, which is parallel to the boundary, and one is vertical, which is normal to the boundary. Okay, because if you look at this boundary and this component, they are exactly parallel. If you look at this component and this boundary, it is perpendicular. Okay, we call the parallel component as tangential component. And we call the perpendicular component as the normal component. So this decomposing, when which you are separating it as parallel and perpendicular components, can be done for both E1 and E2. Okay, so if I draw the boundary again, I can have the electric field like this and electric field like this. And this is the net electric field. This is E1. This is E1T. This is E1N. Similarly, at the other medium, I can have this is E1N. Sorry, this is E2N because this is in the second medium. This is E2T, and this is the net electric field E2. Okay, fine. And we have all the other values that this is epsilon1 having permittivity, this is D1, this is epsilon2, D2. Remember, the value of D1 is equal to epsilon1 E1, and the value of D2 is equal to epsilon2 E2. So if E1 can be decomposed into E1T and E1N, we can always decompose D1 as D1N and D1T, and also we can decompose D2 as D2N and D2T. Now, what is the relation between E1N, E1T, and E1? Basically, this is a vector addition. So I can write E1 as the sum of the tangential component and the normal component. Similarly, I can write E2 as the sum of tangential component E2T and the normal component E2N. I can write D1 as the sum of its tangential component and its normal component. Similarly, D2 as sum of its tangential component and its normal component. And this is the one which we are going to make use of. Okay. Fine. Now we are also going to fix some directions. Okay. We say if you move, if you are looking at this direction, this is positive. Means the opposite direction is negative. And we also say if you are going down, or I would say if you're going up, I put it in different line. If you are going up, this is positive. If you are going down, this is negative. So these are some directions we are going to fix. Okay. Fine. So let me copy this. Okay. So now, basically, we want to find out what is the relation between E1 and E2. What is the relation between E1, or I would say E1T, E2T, E1N, E2N, similarly for D1T, D2T, D1N, D2N. So how are all these things related? Okay. So for that, we are going to consider a small area or a surface. Okay. So let's consider a rectangular surface like this. It's a very, very small surface or a very, very small area or a path. We would say it has a path. It's a rectangular path. The path is from A to B to C to D. So if I draw the directions, it will be something like this. A to B, B to C, C to D, and D to A. So this is a closed path. And we have already derived an expression of a vector or a potential or integral E dot dl is 0 in a closed path. We'll see that. Let the distances is, let's say this is delta h by 2, this much distance, and this is delta h by 2, this much distance. Okay, and this distance is delta w. Right? So your dl, or will directly do this integration, integral E dot dl is equal to, let us travel from A to B. If you travel from A to B, the dl value, since the path is very, very small, we say the dl value is delta w. Okay. And you see that since this is a dot product, only those electric field component which is parallel to this path will exit. Okay. So only parallel, or I would write in bit more easier way. So since it is a dot product, or the electric field components perpendicular to dl becomes 0. What do you mean by that? If you consider E2t, the tangential component E2t, this is parallel to this dl, right? Because both are in the same direction. So if you do E2t dot dl, then it is magnitude of E2t into magnitude of dl, which is delta w, multiplied by cos 0, which is 1. So basically it is E2t. I write that. So if you do E2t dot dl, it is equal to E2t multiplied by delta w, its magnitude, into cos theta, which is 0 degree, that is E2t, magnitude of E2t into delta w, because delta w is a scalar. Okay. Now, if you do E2n dot dl, for this is for the sides A, B, it is E2n, its magnitude, delta w, its magnitude, cos 90 degree. That is the magnitude of E2n into delta w into 0, that is 0. So the perpendicular components will vanish. Okay. And when you are saying you are doing an integration, integral E dot dl is equal to, I can say, integral A to B E dot dl plus integral B to C E dot dl plus integral C to D E dot dl plus integral D to A E dot dl. And this is a closed loop integration or closed path integration. So this value should be 0. That we have already proved at the starting of this lecture. Okay. So when I do integral A dot B E dot dl, we already proved that AB is in the second dielectric, whose electric field is E2. This was is E2 dot dl. And we have decomposed E2 as E1, E2t plus E2n. So I can write this as integral A to B E2t plus E2n dot dl. So this I can expand as integral A to B E2t dot dl plus integral A to B E2n dot dl. Okay. Now we have seen that E2n dot dl is 0 because along A to B this is 0, and this is equal to the magnitude of E2t into delta W, right? Okay. Now let us consider the next part, which is this one, B to C. Remember, B to C is downwards, which means it will become negative. Okay. So if I do integral B to C E dot dl, I have two parts. The first part is where it is in the first medium, and the second part is where it is in the second medium. Okay. So I can split this as integral B to, let's say this point is C dash. Integral B to C dash E1 for E2 dot dl plus integral C dash to B E1 dot dl. Right. So the first part I can split as B to C dash E2t plus E2n dot dl, and the second part you can split as C dash to B E1t plus E1n dot dl. Okay. Now there is a catch. If you look at the edge here, the vector, the component of electric field which is parallel to this one is the normal vectors. The tangential vector is perpendicular to this side. So the tangential vector will just disappear because it is perpendicular, and the normal vector only will come into picture. Okay. So I can write this as E2n, its magnitude, dot dl, the delta distance is delta h by 2 because this is delta h by 2. Okay. The next is also delta h by 2, but from C dash to C. So I can write this as plus the magnitude of E1n into delta h by 2. And remember, this is in the downward direction. So there is a minus sign at the starting. So this is with a minus sign. Okay. Similarly, if I do integral B to D E dot dl, you see this is in this direction, and we have taken this direction as negative. So this is minus B to D E dot dl. So this is purely inside the first medium. So this is E1T into delta W. This is a minus sign. Similarly, if you do integral d to a E dot dl, the same way that we have did for B to C. So this will be without a minus sign. So is E1n into delta H by 2 plus E2n into delta H by 2. Okay. So we have the results 1, the result 2, the result 3, and the result 4. Okay. So remember, when I did for the next side, this is negative direction. So minus integral C to D into the component parallel to which is E1T multiplied by the differential distance delta W. When I did D to A, you have two regions. This is delta H by 2. This is also delta H by 2. Okay. And this is in the upward direction, which is positive. So from D to this point, this is the parallel component is E1n, which is positive into delta H by 2. And from this point to A, the parallel component is E2n, which is delta H by 2 multiplied by delta H by 2. So that is what I have written here. And if you add everything, 1 plus 2 plus 3 plus 4, that should be equal to 0. Why? Because we already proved that this is a closed path, and for closed path, integral E dot dl is equal to 0. So I can write this as magnitude of E2t into delta W minus magnitude of E2n into delta H by 2 plus magnitude of E1n into delta H by 2 minus magnitude of E1t into delta W plus magnitude of E1n into delta H by 2 plus the magnitude of E2n into delta H by 2. This should be equal to 0. Fine. Now we are going to make an approximation. If you see this rectangular path, what should be done to make this rectangular path equivalent to a boundary? Basically, you want to make this rectangular path a straight line. What should we do? If you decrease this height from both ends, means if you make delta H tends to 0, so this shrinks to the boundary, or it will come equivalent to the boundary, right? And equivalent to the boundary means basically it is the boundary itself. So by doing that, you will be able to find out the electric field values. So what we are going to do is let delta H tends to 0, implies it will become the boundary. The path will become the boundary. So if you substitute delta H tending to 0 in this equation number 5, we will get E2t into delta W minus E1t, the magnitude, into delta W is equal to 0. Or we can cancel delta W, the magnitude of the tangential component of both the electric fields are same once you cross the boundary. This is the first boundary condition. Okay. What does it mean? The tangential component of the electric fields are continuous across the boundary. So if the electric field in the first medium is, let's say, 5 volt per meter, the tangential component of electric field is 5 volt per meter in the first medium, then the tangential component of electric field in the second medium will also be 5 volt per meter. Okay, so this is the first boundary condition. You can always write electric field E2T magnitude is basically the magnitude of epsilon 2 D2T, right? So similarly, I can write the magnitude of E1T is equal to epsilon 1 D1. So if you substitute this, you see the magnitude of epsilon 2 D2T is equal to the magnitude of epsilon 1 D1T. Or I can write this as epsilon 2 D1T into the magnitude of D1T by the magnitude of D2T is equal to epsilon 2 by epsilon. So this says, so this is actually the next boundary condition. It says the electric flux density is discontinuous. The tangential component of electric flux density is discontinuous because there is a multiplication factor of epsilon 1 or epsilon 2 across the boundary. Okay. Fine. So we have found out how the tangential component of electric field and the electric flux density varies across the boundary. We have one more component, which is the normal components. To find out how the normal component varies, we construct a cylinder. Okay. And this cylinder has delta H by 2 height in the first boundary across the first medium and delta H by 2 height in the second medium. Okay. The surface area of the circular part, let's assume it is delta S. Okay, so this is also delta S, this is also delta S. And we have already told that the direction of the surface is perpendicular to the surface and away from the surface. Okay, so this is the direction of delta S. We told that we have the components of D, which is D1T, this is D1, sorry, this is second medium. So I have D2T and D2N. Basically, this is my net D2. And in the first medium, you have D1T and D1N. And this is my net. Okay. So if you, here we are going to make use of our Gauss law, which is integral, surface integral, d dot ds is equal to rho s into ds, or q enclosed. Q, which can be written as integral rho s ds. Okay, because we have already seen if you integrate surface charge density with the surface area, you will get the charge enclosed. And if you see this, if you look at integral surface integral d dot ds, again the parallel component of the surface is along this direction. The parallel component of surface is d2n, okay, and the perpendicular component is d2t. So the perpendicular component will vanish, which is d2t, so only the parallel component will survive. So you can write this as d2n, its magnitude, multiplied by the surface area. The surface area is here delta s. This is the surface area of this surface and the surface area of this surface. So this is into delta s. And if you consider the next surface, you see the surface is in this direction, which is opposite direction. Okay, and the parallel component is d1n. Both are in the opposite direction. So I can write this as minus d1 into delta s. Okay, so there may be components of d along this surface, all along this surface. But what we are going to do is we are going to shrink this surface, make delta x tends to 0, because of which whatever be the components on that cylindrical surface will vanish. Okay, so I can write, since delta s will tends to 0, implies it is a boundary, whatever components is on the curved surface will vanish. This we have seen in the previous example, right? Because wherever there is a multiplication of delta h, it just goes to 0, because you are making delta h tends to 0. So I am not considering anything of that of delta h. So finally I can write mode determinant, or the magnitude of d2n into delta s minus the magnitude of d1n into delta s is equal to, now rho s into ds, I can write this as rho s into delta s, because delta s is the surface area. So I can write this as rho s into delta s. So we will come to our next boundary condition, which says the magnitude of d2n minus the magnitude of d1n is equal to the surface charge density. Or if the surface charge is equal to 0, implies the electric flux densities normal components are continuous. Similarly, I can write D2N as in terms of E2N. So I can write this as E2N by sorry. So this is as epsilon 2 E2N minus epsilon 1 E1N is equal to derives. So I think I made a mistake in one part here, which is basically this is actually d2t by epsilon 2, and this is basically d1t by epsilon 1. So I can write this as this is epsilon 1, this is epsilon 2, this is epsilon 1, and this is epsilon. Okay. So these are the boundary conditions that we derive using the electrostatic equations. Okay, fine. So I think we will not have enough time to look at the Laplace and Poisson's equation. That we will do it in the next class. It might take only 5 or 10 minutes, and then we will go to the magnetostatics. Okay.